All right, let's start. So, hello everyone. I'm Wanxin.
Hi, I'm Shayon.
Today we're gonna present you our Kaggle image recognitions project, which is the Benga character recognitions. You can also visit our blog post via the link here. So, I'm Wanxin. Right now, I'm a master student in data science at Brown University.
And I'm Shayon Shamunto. I'm a PhD candidate in material science, but I also love to dabble with data science every once in a while. And I speak Bengali, fun fact.
Yeah, which adds a great advantage to our teams in this game. So first, I'll start talking about the Kaggle competitions and what we're trying to solve here, and later following with a exploratory data analysis and image preprocessing. And later, we're gonna talk about the models that we're gonna use and how we build the architectures of a model and the model performance. So this is the Kaggle competition Bengali AI handwritten grapheme classification. From the left graph, you can see there's a typical Bengali characters, which is composed by three components, which are the grapheme root, vowel diacritics, and consonant diacritics. Altogether, there are 168 class of grapheme root, 11 class of vowel diacritics, and 7 class consonant diacritics. So our task is to predict from the image of the characters what is the characters belongs to, like which class of the grapheme root and which class of the vowel diacritics and the consonant diacritics. And next, let's go to the EDA parts. Here we can see there are mainly three target classes, which are the grapheme roots and the vowel diacritics and consonant diacritics. The left of the graph shows the number of images per grapheme roots. Here are the top 10 most popular, and the right graph shows the 10 least popular. And visually, we also plot the grapheme roots. You can visualize the top 10 common grapheme roots and also the least popular grapheme roots here. And here's the top 10 most popular vowel diacritics. We also plot the distributions of the number of image per vowel diacritics. You can see nearly 42,000 image are lack of the vowel diacritics. This is a pretty much like an imbalance of the vowel diacritics here. It's actually not because of the data collection problem. It's just the nature of the Bengali language, which means like most of the characters only compose of the grapheme roots and also the consonants diacritics. Next, we move on to consonant diacritics. Altogether, we have like 7 different consonant diacritics. Let's see the distributions. We can also observe the imbalance here, and that also talks about like most of the characters does not have the consonant diacritics and only composed of the grapheme roots and the vowel diacritics. Next is the image preprocessing parts. We have already handwritten image, and that means some image might have the problem of like opacity, or some image might have the problem of the centering problem. That means some character does not locate at the center of the image, and that would add some complexity or difficulty for us to classify the characters. And that's why we need the preprocessing. We introduce 4 steps in our preprocessing blocks. The first part is to remove the noises. We use the OpenCV's non-local means denoising to remove the noise. And second part is a grade scaling. Basically, we just save the image as the original grayscale image. And then we would have the thresholding if as a certain pixel values. If the pixel values is lower than the threshold, then we just reduce it to 0. If the value is higher than this values, we just set it to 255. The last part is the contouring and reshaping. We just use the contours and then recognize the characters and then put a bounding box around the characters. Later, we just do a rescaling and rescale it to a 64 by 64 square. You can also see some simple sample code snippet here where we include all 4 parts of the pre-processing steps. Here's the contrast of the pre-processings and then after pre-processings. The difference is pretty obvious. First, we reduce the opacity problem and we also center the image and make it more easier to classify it. Next, we're going to talk about the model. The basic model that we use is the CNN, which is the convolutional neural networks. Let's first imagine that we want to recognize a cat in an image. It's actually pretty inefficient if we just associate the positions with the features of the image, because in this way, the cats on the right top corner is different than the cats on the left bottom corner, right? And it's not really like machine friendly, then it will not associate with these two images as the same thing. That's why we want to exploit the concepts from the human visual cortex, where each neuron is actually associated with recognizing a specific features. And each neuron would learn the features regardless of its position. And this is also what exactly the convolutional layers does. Is spatially invariant, where each layers could learn the specific features. For example, one layer would learn the specific the grade stroke, and then the next layer would learn whether it's verticals or horizontal. Then we have a stack of simple layers, and also have like more complex layers to learn the complex features. Then once we have the outputs of this layer, and then we would send it to the pooling layer. What the pooling layer does mainly are 2 things. The first thing is feature selections. It would select the best combinations of the simple features and the complex features. And the second part is just do the downsampling. Now, what about let's just have like thousands of layers of convolutional neural networks? Does it work? Well, technically it works, but the signals from the initial inputs would actually get weakened and weakened as we develop more deeper convolutional layers, right? To tackle this problem, in 2016, Gao and his colleagues developed the dense nets, which is the densely connected convolutional neural networks. From the graph, you can see every input of the next convolution layers is actually are the outputs of all the previous convolutional layers. And you can see the red lines are the connections from the previous layers, and then every successive layer has the knowledge of the inputs to its preceding layers. So what it does is to preserve the signal from all the previous layers, and it also preserves the features and also avoid the vanishing or exploding gradient descent problem, while it also does the strengthening feature propagations and reuse. Then once we have the dense nets, what about let's just stack thousands of the dense net together? Well, now we also have the problem because it's memory inefficient. Why? Because it's barely possible to let the machine memorize every layers of the outputs and then feed it into the inputs rates. Then we have the solutions here. Gao and his colleagues developed the concept of dense block, where it just puts the densely connected neural networks into a chunks or into a blocks, where the block cells is just doing the inputs and get the outputs of all the previous convolution layers and feed to the inputs of the convolution layers. And then they have the outputs to fit into the transition block where it does this downsampling through a one by one convolution layer and then to do a average pooling to achieve the desired dimensions. So this is our basic architectures, but does it really work? Let's go back to the post.
Oh, yeah. Well, we can be like adult Lego players with our neural network architectures, but does it really work? Well, in this case, I guess it does, because if we compare the images that are shown here, for a given error, the same error is achieved by a dense net in a with a number of parameters like 2 to 3 times less than a ResNet model at the same accuracy. Likewise, we can also see that a dense net takes almost 2 to 3 times less number of floating point operations to receive the same amount of validation error. Therefore, so far, the signs that it shall work is really well. Something to note that is very suited for a grad student project, because we really do not have the resources to run our neural nets for hours and tons of GPUs. So dense nets seem to be a good fit for the problem that we're planning to challenge. Going very specifics into our version of the dense net, we have input layer, which takes in the images and as a form of 64 times 64 times 1 format, because all our images are grayscale. We do have the option for adding an augmentation layer, but we have not done it for this particular run, but it's something that we plan to get back to in the future. The major workhorse of our dense net is the dense blocks. We have 3 of them. In each dense block, there is 4 convolution layer, each layer having 12 filters, the 4 convolution layers are followed by a transition block where we do an average pooling of size 2 cross 2 followed by strides of 2 cross 2 to downsample our output dimension. Finally, at the end of the third dense block, we have a global average pooling layer, which collects all the feature information that these dense layers and the convolution layers have obtained, and then pass it along through a 3 output dense layer, one for each target. It must be mentioned that all throughout, like at the end of most convolution layers, we do have dropouts and batch normalizations to reduce overfitting and also ensure proper signal strength. In total, for this network, we have a total parameter of 173,000, well, of which 170,000 are roughly trainable, while the remaining 3,000 are non-trainable. About the other hyperparameters, we use the Adam optimizer with a starting learning rate of 0.01. Adam, by the way, is a variant of the well-known gradient descent optimizer. The loss function for this project, because since each value is just a label with no numerical significance, we use the sparse categorical cross entropy as our loss function for all the outputs. Excuse me. Although the competition webpage measures a weighted recall metric, for the purpose of training, we use the accuracy metric because, first of all, it's easy to design on the network, and secondly, we believe that it is a much more stricter metric to train our network on. Last but not the least, we did use a variable learning rate for this problem, and we calling TensorFlow's native reduce LR on plateau on all the 3 output, where we start off, as I mentioned, with a learning rate of 0.01, but then reduce by a factor of 0.2 each time a particular loss plateaus to the minimum learning rate of 10 to the power minus 4. As Wanxin mentioned, our data set is highly imbalanced, so we chose to use scikit-learn's train test split and stratified fashion, having equal class weightage on both the validation and the training set. Basically, we divided it into 90% on the training and the remaining 10% of the validation. We chose a batch size of 32 and trained our model for a total of 100 epochs. From the outputs look really promising. In the vowels, we achieve a training accuracy of 98% while the validation accuracy of 97.5%. On the root, which is the most difficult of them all, there are 168 of them, mind you, we almost reach an training accuracy of 95 and a validation accuracy of close to 92 or 91, to be very honest. And for the consonants, we have a training accuracy of close to 98 and validation accuracy of close to 97%. We are excited with these results, but then there are more steps to go. The next step would be to tune the hyperparameters, which could squeeze out further accuracy from a project. What's also interesting to check is that if we don't leave it on the last single output layers to make sense of the inputs from the conv layers, we could perhaps add a couple of dense layers to give a more wiggle room to get a better output. We also think that image augmentation during training will definitely reduce overfitting and might improve accuracy. With all that said and done, thank you for listening to us. It was a great time speaking and doing this entire project. All the codes, by the way, can be found on the GitHub repository that has been linked at our blog. Thank you so much.
Thank you. Thank you for listening to us. Where's the good time? Why is it not here?
I don't know.
What? Why did it just disappear? Did we not record it?
I think we did, but just close it. Just close everything. And it should go.
Okay, wait. I need to charge it.
I see. I'll try to find our